All right, so in this video lesson, we're going to be talking about two different concepts. The first is going to be the idea of what are called percentiles. The second is then going to be about what are called z-scores. So to start off with, a percentile, the definition for that is that it is the percent of the scores or values that fall below a particular score. In other words, you're looking at what percent of people did worse than a particular score. So we're going to talk about that in regards to the 5-number summary. So if you think about it, the minimum, that would be 0%. There would be nobody that would score below the minimum. So that would be the 0th percentile. So rather than writing percent, I should say 0th percentile. So quartile 1, that's the first quartile. Quartile, think about quarters. A fourth would be 25th percentile. Median is halfway, so that would be the 50th percentile. Q3 is your third quartile, so that would be the 75th percentile. And while you think the maximum would be the 100th, it's actually not going to be the 100th percentile. It'll either be, the 98th or maybe the 99th, but there is actually no such thing as the 100th percentile. And if you think about it, it's because you can't score higher than everybody, including yourself. And so that's why if you've ever seen like your standardized tests, maybe you got your test results from the ITBS or any of those different elementary school kind of tests, the highest you can get is the 99th percentile. There is no way to get the 100th percentile because you can't score higher than yourself. So when I say it's going to be close to the 100th, 98th, 99th, it might be 97th. It just depends on how much data is in the sample. So on a particular test, is a student's percentile the same as the percent correct? The answer is usually no. It is possible for them to be the same. So it is possible to say get a 60% on a test and be in the 60th percentile, but it usually is not going to be the case that the percentile and percent are the same. All right, so let's take a look at an example of this. So the stem plot below shows the number of wins for each of the 30 Major League Baseball teams in 2009. So you've got your stem plot, you've got your key over on the right. Let's go ahead and calculate and interpret the percentile for the Colorado Rockies, who had 92 wins. So you had 92 wins is right here for the Colorado Rockies. And let's go ahead and find their percentile. So what we're interested in is how many teams did worse than the Rockies. So if you count those up, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 24. So 24 out of 30 teams did worse than the Colorado Rockies. And so then if you type that into your calculator, 24 divided by 30 is going to be 0.8 as a decimal. So that would be the 80th percentile. Now, as far as interpreting, so that would be your calculate. But to interpret, we would say that 80% of MLB teams did worse or had less wins. I'll go ahead and write it that way. So had less wins than the Colorado Rockies. All right, so let's take a look at a couple more examples. Let's go ahead and look now at the New York Yankees, who had 103 wins. So they are the very top team. What that means is that if there were 30 teams in total, then the New York Yankees did better than 29 out of the 30 teams. Not 30 out of 30, because they can't do better than themselves. This is what we were talking about, that they're actually, even though they're the best team, not going to be the 100th percentile. In fact, if you take 29 divided by 30 is 0.96 repeating, it turns out that they're actually only the 97th percentile. So they're not even the 99th percentile. And that's just because of the number of teams that were in Major League Baseball. And so your interpretation, I'll go and write this interpretation slightly different from the last, is that we would say that the New York Yankees had more wins than 97% of the Major League Baseball teams. All right, one last one to look at. Let's take a look at the Cleveland Indians, who had 65 wins. So Cleveland Indians. Now, 65 actually happens twice. But here's the thing to think about. Really, 65 isn't lower than itself. And so it doesn't matter which one you pick. In fact, it's usually best to just group them up together. And then we look at the fact that there are 1, 2, 3 teams that did worse. So for the Cleveland Indians, we'll take 3 out of 30, which ends up being a pretty nice number. Ends up being 0.1, so they are the 10th percentile. So again, the interpretation for that is that the Indians had more wins than 10% of the other teams. And so each of our interpretations was slightly different, but notice that they're all saying the same thing. Like for the Rockies, when we said that 80% of MLB teams had less wins than the Colorado Rockies, you could rephrase that and say that the Colorado Rockies had more wins than 80% of the MLB teams. And then, yeah, you could also change the Yankees one to say that 97% of Major League Baseball teams had less wins than the New York Yankees. You'd be saying the same thing as that the Yankees had more wins than 97% of the MLB teams. So you've got kind of a few different ways you can word your interpretations as long as they are worded correctly. All right, so now we're going to talk a little bit about what are called z-scores. So to kind of lead this into this idea of what a z-score is, let's talk about Macy. She's a 3-year-old female and is 100 centimeters tall. Brody, her 12-year-old brother, is 158 centimeters tall. So obviously Brody's taller than Macy. I mean, he's 12 years old versus a 3-year-old. That shouldn't be surprising. But who's going to be taller relatively speaking? That is, relative to the other kids of similar ages who would be taller for their age group. According to the Center for Disease Control and Prevention, the heights of 3-year-old females has a mean of 94.5 and a standard deviation of 4. Whereas the mean height for 12-year-old males is 149 centimeters with a standard deviation of 8 centimeters. So let's just talk about Macy first. So we already know Macy's 100 centimeters tall. Now the average for her age group is 94.5. So if you think about it, if you take 100 minus 94.5, we know that for Macy, I'll just put an M over here, that Macy is 5.5 centimeters taller than the average for her age group. Let's compare that to Brody. So for Brody, we know that he was 158 centimeters tall and that the average was 149. So if you take 158 minus 149, we know now that Brody is 9 centimeters taller than the average for his age group. But here's something else that we need to consider, is not just are they above average or below average, but how far above average and how far below average. And we have to do that kind of comparatively, because if you think about it, when you're thinking about the heights of teenagers and adolescents, like a 12-year-old, those are going to probably be a lot more spread out with kids who have had their growth spurt, kids who haven't had their growth spurt, whereas the heights for a 3-year-old probably are not going to be as far spread out. And remember, when we're saying that word spread out, really what we're talking about is the standard deviation. And so if Macy is the standard deviation of 4 centimeters for her age group, if we take the 5.5 that we got and divide by 4, what we're going to find out is that Macy was 1.375 standard deviations above the average, or above the mean. Let's compare that to Brody. So for Brody, the standard deviation was 8 centimeters. So if we take 9 and divide by 8, we get that he was 1.125 standard deviations above the mean. So if you think about it, relatively speaking, Macy is actually taller for her age group. And actually, this is going to be the idea behind what we're going to talk about next, which is the idea of what's called a z-score. So let's first talk about the formula for a z-score. In order to calculate a z-score, we're going to take our value for our sample, so x, minus the mean for our sample, so x bar, over the standard deviation. And the same would still work if you had population values, so x minus mu over sigma sub x. That would work as well. Now again, the one that we will primarily be using is this first one, because remember, very rarely do you have population values, but the same formula would still apply. So the z-score, a way to think about that, it is the number of standard deviations either above or below the average. So let's talk a little bit more about that idea. So do z-scores have units? The answer to this question is no, they do not. However, what does the sign of a standardized score tell you? So another way to think about a z-score as a standardized score. And so if it's a negative, that implies that it was a below average score. If it's a positive sign, that implies that it's above average. So negative is below, positive is above. So then what does a score of 0 mean? That you were right at the average. So you scored exactly on the average. Now, that very rarely will actually happen. Most of the time you're slightly above or slightly below. Remember, the average very rarely is one of the values in the data set. So very rarely do you actually have a z-score of 0, although it could possibly happen. All right, so for this next example, let's do some practice with finding z-scores for some students. So we've got 25 students in Mr. Pryor's stats class. Here are their scores on the first test. And we want to know what Jenny's z-score is in this first part if she scored an 86. So we need to find a couple of things first. We need to find our mean and our standard deviation for this data set. So let's go ahead and do that right now. So I'm not going to put a calculator on the screen. I'm going to trust that you remember how to do this from Unit 2, but let's get all of our data typed in, and then we'll find those values. Okay, so here's what I'm coming up with for our mean and standard deviation. The mean actually wound up being a whole number. It was right at 80. And then for the standard deviation, I'm coming up with 6.07. All right, so let's find Jenny's z-score. It looks like she scored an 86. And so if we're going to find that, the z-score for Jenny, and I'll write that as z sub j, we're going to take her score, which is 86, minus the mean, which was 80, divided by the standard deviation, which was 6.07. And when we do that, so 86 minus 80 divided by 6.07, let me go ahead and type that in again. I'm coming up with a z-score of 0.988. So she, it looks like, is just below 1 standard deviation above the mean, which should make sense. If you take your mean plus 1 standard deviation, that would be 86.07. She scored an 86, so just a little bit less than 1 standard deviation below the mean. Let's next talk about Katie. So Katie, it says, had the highest score in the class. So let's see what the highest score in the class was. I'm going to go ahead and sort my data in my calculator. And it looks like the highest score in the class was right at a 93. So for Katie, I'm going to go ahead and do z-score for Katie. We're going to take the 93 that she got minus 80 and divide that by 6.07. So let's go ahead and do that now. That ends up being 13 divided by 6.07, which is 2.14. So she was about 2.14 standard deviations above the average. Last, let's go ahead and do Norman. Unfortunately, Norman had the lowest score. And so looking at our data, it looks like 67 is the lowest score in the class. So let's go ahead and find Norman's z-score. So we'll take 67 minus 70 divided by 6.07, which ends up being the opposite of the last one, so negative 2.14. So it looks like Norman was a little over 2 standard deviations below the average. So remember, a positive z-score means that they're above average, negative that they were below average. All right, for the last part, the day after receiving her statistics score of 86 from Mr. Pryor, Jenny earned an 82% on Mr. Goldstone's chemistry test. Mr. Goldstone told the class that the distribution was fairly symmetric, had a mean of 76 and standard deviation of 4. Let's go ahead and find the z-score for Jenny's chemistry test. So that would be taking her score, which is 82, minus 76. So she was once again 6 above the average, and divide that by 4, which ends up being a z-score of 1.5. So relatively speaking, we would have to say that Jenny did better on her chemistry test. Now, looking at the actual grades, yeah, she did have a higher score on the stats test, but relative to her classmates, it looks like Jenny did a little bit better on the chemistry test. All right, let's take a look at one last example of this to kind of see how this works, and then we'll be done with this video. So the single season home run record for Major League Baseball has been set just 3 times since Babe Ruth hit 60 home runs in 1927. Roger Maris hit 61 in 1961. We already had heard about Mark McGwire, who hit 70 in 1998. And now let's throw Barry Bonds in there, who hit 73 in 2001. So in an absolute sense, Barry Bonds has the best performance of those players because he hit the most home runs in a single season. But relatively, that might not be true. In fact, the historians for baseball suggest that hitting a home run has been easier in some eras compared to others. And this is due to a lot of factors, including the quality of the batters, the quality of the pitchers, the hardness of the baseball, the size of the ballparks, the use of drugs like steroids. So there's a lot of different things to consider. So to make it a fair comparison, we should see how each of these performances rate relative to other hitters during that same year. So let's go ahead and calculate the standardized score for each player. Let's go ahead and start with Babe Ruth. So our z-score for Ruth. So for Ruth, he hit 60 home runs, minus the mean. The average for that year was only 7.2. And then divide that by our standard deviation of 9.7. So when we do that, 60 minus 7.2 and divide by 9.7, we get that Babe Ruth was a whopping 5.44 standard deviations above average. Next, let's go ahead and find the z-score for Maris. So for Roger Maris, he hit 61. The average that year was higher than it was for Ruth, so 18.8, and standard deviation was 13.4. All right, so calculating that, 61 minus 18.8, dividing by 13.4, I'm getting that 3.15. So he hit still above average, but not quite as far above average as Ruth did. Next, let's do McGuire. So for Mark McGuire, he hit 70 home runs. The average continued to go up, was 20.7, and then divide that by our standard deviation, which was 12.7. And when we do that, we end up with a z-score, which is higher than Maris's, 3.88, but still definitely below Ruth. Let's last take a look at Bonds. It's the most recent home run leader. If we take 73 minus the average of 21.4 and divide by 13.2, we end up with a z-score of 3.91. So he would be the second highest, but it looks like, relatively speaking, Ruth is the best hitter. All right. Now this next example is going to be super important because there is going to be multiple questions on the homework, and I would assume the quiz and test that will be like this. And so what we want to be able to do is to also be able to work backwards. So in 2001, Arizona Diamondback Mark Grace's home run total had a standardized score of z is equal to negative 0.048. We want to interpret this value and then calculate the number of home runs he hit. So we would say that Mark Grace's home run total was 0.048 standard deviations below average. So remember, below because it was a negative 0.048. Now let's go ahead and see how many home runs he actually hit. So remember, our formula is we'll take x minus x bar and divide by standard deviation. Now, we already know z because we were told that his z-score was negative 0.048. To find the rest of the information we need, we're going to go back up to that table and look at 2001. So 2001 was the year that Barry Bonds was the home run leader, and that had a mean of 21.4 and standard deviation of 13.2. So x bar, again, was 21.4. Standard deviation was 13.2. So let's plug those into the formula as well. So we still don't know what x is. That must be what we're solving for. Minus 21.4 divided by 13.2. All right, so to solve for x, let's go ahead and start by multiplying each side by 13.2. And when we do that, 13.2 multiplied by negative 0.048, coming up with negative 0.6336 is equal to x minus 21.4. All right, so then to get x by itself, let's go ahead and add 21.4 to both sides. And I'm getting that x is equal to 20.7664. But again, we're talking about home runs, so it looks like Mark Grace hit 21 home runs in total that year. All right, that is all I've got for us in this video lesson. Until next time, have a great rest of your day.